Hello, we are Group 2 and we are doing a performance comparison of in-memory database management systems. Our group is Khaled, Bryant, and Jessica. So as an outline, we are going to go over the introduction. We'll do related work about our databases. We will show our proposed work of the YCSB benchmark system, our Python data processing, the benchmarking, our results, and then we'll go over our conclusion, future work, and then we'll show a demo. So as an introduction, the evolution of data-driven applications has led to the need for quicker data access. In-memory database systems do not rely on disk storage, so they are faster and more efficient than disk-based database systems, as the memory is much easier to reach. With differing options of in-memory databases, it is difficult to choose the ideal candidate based on the needs of the developer or the user. So as that is a problem, we have this study is intended to alleviate and perform comparisons of 3 of the most popular in-memory database systems. We have Aerospike, Memcache, and Redis. We have selected these databases based on their high-profile customers such as Aerospike's PayPal, Adobe, and Verizon Media, Memcache's Facebook, Instagram, and Twitter, and Redis's GitHub, Pinterest, and Snapchat.
So disk-oriented databases depend on disk as the main storage, and they have been dominant for decades. However, the I/O latency is a bottleneck for these systems because of the extremely slow disk access. Given the availability of high-capacity main memories such as DRAM, now in-memory database systems have emerged, where the entire database can fit in main memory, which of course provides faster access to data and more predictable performance. We chose 3 in-memory database systems to evaluate in this project. The first one is Redis, which is an open source data structure store in-memory database. It also provides optional persistent support in case data needs to be persisted to disk. It provides support for a wide variety of data structures such as strings, sets, hash, and lists. It also implements replication, sharding, and clustering, and it provides support for range queries, transactions, and geospatial indices. It also works only on a serialized execution environment.
Looking at the features of one of our databases, Aerospike, it is a row-oriented database with key value pairs. It has built-in clustering. It is compatible with flash SSDs, unlike the other 2 databases. Uh, they feature 5.9 uptime for the data accessing. They provide automatic sharding for data localization. For smaller data segments, there is a lower operating cost. And for dynamic data inconsistencies, when we're trying to read and write lots of changing data, it forgoes the cache and relies on high throughput and low latency to write to the database directly.
Just like Redis and Aerospike, Memcache is an in-memory database system. It's a simple key-value storage system, so things are not stored in objects like strings or lists. When a Memcache server is initiated, it allocates a portion of the computer's RAM. By default, Memcache starts with a small amount of memory, and we actually had a problem with this. We had to specify a larger amount of memory in order to run our benchmark. Memcache databases are also only capable of handling simple operations like getting and setting values. This is a downside when comparing to the other databases. And multiple Memcache servers can be used together. However, they are isolated, meaning you cannot replicate data. Also, memory on every Memcache server is temporary. Whenever you set something, it will go away in a specified amount of time. It is designed so the most used items stay around the longest. We tested our databases through the Yahoo Cloud Serving Benchmark, or YCSB for short. The YCSB client first takes commands from the command line. Next, it generates instructions from the workload. Then, it runs those instructions on the database. Lastly, the statistics generated from that run are sent back to the command line. The command line is how we run YCSB. We give it parameters such as the workload to use, how many threads to use, how many records to insert, and so on. This is also where we must specify the database to use. If we don't give the proper address of a database that is running on our machine, then YCSB will not work. Now, the YCSB client itself is actually a Java program. It was created by Yahoo to measure metrics like latency and throughput from the database. It contains many modules that will interact with the workload, database, and the command line. I will explain those modules in detail later on. Workloads are files that contain instructions and records to send to the database. YCSB comes with several predefined workload files. These contain read, write, update, and scan queries. The YCSB literature implied that these workload files were contained outside of the client. In fact, it is possible to define custom workloads. The database is also contained outside the YCSB client. In our case, the database was connected locally, but it can be connected over the internet. There are two phases that the database should see when running a workload. The first is the load phase, which loads records into the database. Next is the run phase, which runs queries on those records. Notice that nothing is returned from the database. This was reflected in the YCSB literature. This is because the client's threads measure statistics when executing instructions on the database. The database interface is what actually connects YCSB to the database. The interface takes instructions from client threads and relays them to the database. So this interface serves as just a simple access point to the database from the client. Like was said earlier, the output from the database is not actually kept. It seems like it should be that way since we do run GET operations. However, the YCSB literature did not reflect this. Similar to this interface, the workload executor connects to the workloads. It processes the instructions, the data, and whether to load or run instructions onto the database. It generates all the queries to run and hands it off to the client threads. Like was said earlier, client threads are the items within the client that actually execute instructions. However, they also keep track of metrics like latency and throughput. If there are multiple threads, these metrics will be averaged at the end of the execution. However, for our project, we only used one thread. The statistics generated by the threads are stored as key value items. After YCSB is finished, it is output to the console. This output is how we tested the database performances. Separate from the YCSB system, we actually created a Python program to generate graphs from the output metrics. In this diagram, the workload result processor is our main Python program. It will take in the output from multiple YCSB runs that are stored in the result folders. It will then read in the data as a key value item into a dictionary for each file. Since we run a workload on a database multiple times, we will get the average of these results. For example, if we run workload A on memcached 5 times, we will get the average of that. Then the metrics are outputted to a graph. We account for runtime, latency, and throughput. The generated metrics graphs are then outputted as PNGs.
We evaluated all 3 systems using YCSB. It comes with a different set of workloads. So, for example, workload A has a 50-50 ratio of read and update operations. Workload B is mostly reads. Workload C consists of only reads, and workload D has a 95-5 ratio of reads to inserts. And workload E is mainly scan operations. And finally, workload F has a ratio of 50-50 read to atomic read-write modified operations. So this screenshot shows one of our scripts to run YCSB benchmarks on Redis. So we first specify the different parameters, such as the IP address of the server and port number, and then we have the number of records and the number of operations. And then we actually run the benchmark down here, and we save the results to the statistics. So we use the following evaluation metrics in our experiments. So we used overall latency, which is the total number taken, the total time taken by the workload to finish execution, and overall throughput, which is the total number of operations executed per second. We also capture the average update, read, and scan latency. And the screenshot here is taken from one of the output files generated after the execution of one workload, and it shows the different values for these metrics captured. For our experimental setup, we used record count of 1 million records. Each is 1 kilobytes in size. And we had 1 million operations with each workload. And we ran each workload for 5 times and took the average of all statistics among the 5 runs. And we used the specified versions of Aerospike, Memcached, Redis, and YCSP. And all of the experiments were conducted on the same hardware configuration to ensure fairness, which is this Ubuntu machine with 16 gigabytes of memory and 12 megabytes of L3 cache, 512 gigabytes of disk, and Core i7 processor. So this figure shows the average latency for each of the workloads among the different systems that we have. So we have eliminated the results for workload E because it's mostly scan operations, because both Memcached and Aerospike bindings don't have the scan operation implemented. We can see that both Aerospike and Redis show close performance results, while Memcached shows the worst. This can be accounted to Redis and Aerospike are mainly designed to work in a serialized execution fashion, which was this setting for these set of experiments, while Memcached is mainly built around multi-threaded execution, trying to cover the limitations in their implementation. We can also observe the same trend when looking at the average latency, where both Redis and Aerospike show similar results here, while Memcached remains the slowest. Same we can observe for the update latency among the three systems. So here we don't have the result for workload C, D, because they don't have any update operations. And we can also say the same for the average for the average throughput, or the overall throughput observed in operations per second.
In conclusion, we have evaluated 3 high-profile in-memory database systems using the YCSB benchmarks. We evaluated Aerospike, Memcache, and Redis in comparison to each other. Each experiment was run on a single Ubuntu operating system with similar specifications, or the exact specifications, allocating one node with a single thread. Our statistical measurements included runtime, read latency, update latency, and throughput for each workload. Aerospike and Redis had similar performances in each category, with Memcache performing the worst. To assist with guiding the decision to select which in-memory database is best suited for a given application, from our results, we recommend the following. If you're dealing with large quantities of small data sets, the capability of Aerospike's metadata per record shines better than the alternatives. So if you have a lot of small profiles but a large quantity of them, Aerospike is the ideal. If the data structure is large and complex, so if you have very large data structures and a lot of them, Redis has exceptional performance and is a very good selection. Now, in single-threaded execution, Memcache is not an ideal candidate for an in-memory database. So looking into the future, we can look at running more nodes for the execution of the workloads. So the multi-threaded architecture will help simulate the distributed architecture that each of these in-memory databases support. And in theory, the results could bring Memcache to a more comparable choice, since most of the execution performance relies on multi-threading techniques.
So right now I'll be showing a demo of like running the system, an example of running the systems and generating the results. So there's our terminal here, and in this directory we have the 3 scripts that we use to generate our results. So one for each one for Aerospike, Memcached, and Redis. So we can try Redis. So this is how the script looks like. So first here we are defining the directory or the location to the YCSP directory, which we installed. And then we need the host parameters for Redis, which is the IP address and then the port number to which Redis server is listening to. And then the number of records that we need to load in the load step. So we're using like 1 million records here. So for the sake of this demo, I'll just uh, limit that to only 1,000 because it would take a very long time. And also the number of operations for each workload that we need to run. They were also like 1 million, but I'm gonna reduce it to 1,000 for timing as well. And here the first step is to load the data to Redis. So we need to load these number of records into Redis. And of course, we are specifying the parameters, so, and the number of records. And for each of the workloads, so we have workloads A through F. We go over each one, and we like create the directory for results in case it's not here. Let's say this is not 1 million anymore, so let's delete data, and then the name of the workload. So for example, this I would be either A, B, C, D, or F, and then it would we need to create the directory if it doesn't exist. And then we run each of the workloads 5 times, and eventually we do. This is the run command. So this instead of load, we're doing run. We're specifying the database system here and the workload we're running. And of course, we also pass the parameters like the host information, the number of operations and threads. And we are saving the statistics here with the captured values for the statistics to this file. And we're also capturing the standard error to another log file to make sure that we don't have any errors. So let's save this. And the first step that we need to make sure that the systems, the servers that listening. So we can check the status of Redis here, and we can see that the server is active and running. And here we have the IP address and the port number for the Redis server. Okay, so the server is ready. Then we can just run our script. So Redis sh. We can see here the script is running and some statistics are already generating here. And it's going over each of these workloads, and eventually it will, after it finishes, when we ls in this directory, we'll find that the data or results directory has been created here. We go into it and list it. We can find a new directory for each of the workloads. Let's check, for example, P and ls. We can see 2 different kinds of files. So one kind of the log file, which sees we can open to see if there was any error. So here we can see that there are no errors reported here. So we know that the operation or the process exit normally. There is the other kind of files is the status file where we have the different statistics captured. And here we have, for example, the overall runtime that is in milliseconds, the throughput, the average read latency, the average cleanup latency, the average update latency, and so on. And we have this, we have 5 different runs. So we found files numbers 1, 2, 3, 4, and 5. And we'll have this for each the workloads. Go to A, we'll find the same thing. We can open one of them and status here. And we can see also that we have same information log files. We don't have any errors here. And that is the same for all the different workloads that we have run here. So these are the status for one run. For workload F, we have this. Of course, this is different here because, for example, we have the read modify write operation, which wasn't in workload A or workload B. We have the statistics for that as well.
Hello, we will be showing a demo of our graphing of our results. So once we have run our experiments for each of the workloads 5 times, we put them into text files. So we will have, for workload A, we will have 5 Aerospike workloads, 5 Memcache, and 5 Redis. Looking at one, we will be running the average among these 5 for our graphing function. So here we have 18,382, and here we have 18,064. So among these 5 statistics, we will average them, and then we'll plot them on the figure. And this is done through our main.py, where we originally read in all of our files. There's 15 files for each workload, A, B, C, D, and F. We ignored E because it's scan updates. It's not. It only works for Redis. But we read in our files in main, and then we will average our statistics using our averaging function.py, and then we will graph our functions. The graphs are all in the graph functions.py, but we can debug and show that it's working. So we will be running our 1 million workload. Change the path here. 1 million. So here, this will pull from our 1 million sample file, and then we run our main.py, and it'll show our 4 different graphs. So here's our average update latency, average read latency, average throughput, and our average runtime. And for what we are looking at, our average runtime for Aerospike on workload A was 18,418. So that was the average among these 5 folders.